Okay, so Newton's idea, okay, he developed calculus because he needed it for physics. Okay, Leibniz could see the bigger picture. He could see that this was going to apply to anything that changes, not just physics, but things change in biology, things change in chemistry, things change in economics, things change with disease, things change in, your psychology, your mood, your emotions. Anything that changes can be modeled with calculus. All right, and so that's what we're going to look at today. Geology, okay? Oceanography, okay? All right. So as we kind of wrap up this 2-4 lesson, okay, a rate of change is important to understand that this is an instantaneous moment we're talking about. Okay, we're talking about things that change and are changing at that rate just for that moment that we're looking at, just for that instant. Okay, but we're going to get a little maybe I don't want to say sloppy, but we're going to get a little more casual. And when I say rate of change, the implication is that I mean instantaneous. Okay, I'm not going to say instantaneous rate of change every time. I'm just going to say rate of change. Do you remember the other kind of rate of change we talked about when we started this whole lesson? Average. When I want average, I'm going to say average. Okay, so you'll always should know what kind of rate of change I'm talking about. If I say rate of change, the implication is that it's instantaneous and that you're going to use derivatives to do it. If I specify average rate of change, then you go back to like basic y2 minus y1 over x2 minus x1. No derivatives needed at all. Okay, we good on that? That's going to be the vocabulary we're going to use going forward. All right, so this can apply to geometry. Okay, whoops. It's a good thing I'm not a geometry teacher. How about the word circle? Okay, the area of a circle is, right. Okay, as a function of the radius is area equals pi r squared. All right, so find the rate of change. And so the implication here is to find the instantaneous rate of change. So a circle could be changing. It could be a drop of water and you watch that ripple effect go out, okay, a circle changing like that. It could be a soap bubble. Now we're going to be talking about the sphere itself changing shape, okay? All right, so when we find the rate of change, the implication is here that we want the instantaneous. And so we want to find a prime. All right, so what rule do we need to find a prime?
Product.
Okay, why product?
Oh, because pi is not a variable, it's a constant.
So pi is being multiplied by r squared, okay? The product rule will work. Christian? Okay, the power rule will also work. Okay, the power rule is going to be easier because the power rule is a constant and we can always just take a constant out in front of whatever derivative we want. Okay, and so we remember we did that before. When we saw like 3g, then the derivative, we didn't need the product rule for that. We could say the derivative was 3 times g prime. You only need a product if both parts are variables and if one part's a constant. Now, it's not wrong to do the product rule. You for sure could and it would still work, but you don't need to. All right, so we can just treat this as pi is out in front, and then we just use the derivative using the power rule. And so that's going to be 2r. In other words, 2 pi r. And then what do you know about that from geometry?
Perimeter.
Okay, circumference, yeah. So the derivative of the area of a circle is its circumference.
Wait. Oh my goodness.
Okay. Yes. Okay. Very good. So you're going to see so many connections in geometry. Like, my whole life I've memorized that the circumference is 2 pi r and that the area is pi r squared, but I didn't ever know why. Okay. And that's that. Okay, it works from volume. So what do you think if you do the derivative of the volume, which is how many dimensions? 3. Okay, and if you take the derivative of that, yes, we go. Okay, so now we can start thinking, ooh, could we go to the fourth dimension? Or how do I get to 4? Like, what could I start? Okay, wait, we're getting there. Okay? Okay?
There's like no.
Okay, all right, so then part B. Now evaluate the rate of change when the area is 4, of the area when the radius is 4. And so then we can find A prime at 4. So that would just be 2 pi times 4 or 8 pi. Okay. All right, so the derivative applied to geometry. All right.
My brain.
Okay. The derivative applied to other things that change. Okay, you'll talk about, oh, they're so sensitive. Okay, if somebody is emotionally sensitive, then that means like the smallest thing kind of sets them off, right? It just takes a little bit to just push you right over the edge. Like, oh, I am right over the edge, and the next thing is just gonna, okay? And so in calculus, we call that a high degree of sensitivity. If their rate of change is very high, okay, then that means they change a lot with just a little bit. Okay, a little bit is going to have a big change. We call that how we measure sensitivity, and we do that with derivatives. So go ahead and like highlight that. The derivative will measure what we call sensitivity. So how could that be applied in a real world situation? Okay, so now you're on slide 26. Okay, for example, suppose that you're farming and you're working in agriculture and you know that your crop depends on rain. So your crop is sensitive to the rainfall. How sensitive is it? You want to figure out. So you develop new kinds of corn and new kinds of wheat that need less water so that you're less sensitive overall. Okay, you're working in medicine, you're working in research, and you're trying to develop a new medicine. Okay, and you want to be able to prescribe something to lower somebody's temperature. Okay, ibuprofen, acetaminophen, Advil, Tylenol, Motrin, those kind of things. Okay, well, how much is enough? How much what's the right dosage you would give to achieve the sensitivity that you want? Okay, because a child is going to have different sensitivity than an adult. Why? They have less weight, less body mass. Okay, so you would use calculus to determine that. Okay, so there's another place that calculus could be learned. All right, economics. Okay, if you're interested in going into business or economics or marketing, okay, how sensitive is a certain demographic, a certain community group that you're trying to attract? You're trying to advertise to them. Will they respond to the types of advertising techniques you do? Okay, will they respond well or will they respond poorly? You can use calculus to predict that. Okay, you can predict how you want to set your cost, what you want to set your price level at. Okay, how high can gas go before we all rebel and say, fine, we're all riding bikes, okay, or whatever. Okay, we're all going electric. Well, then how high can electricity go? All right, before we all say, fine, we're going to drive our cars, okay? What's the price point? You might hear that in economics, the price point, like how high can it go before the group that you're marketing to just says we won't take it anymore, okay? All right, so in economics, they don't use the word, so derivative has lots of synonyms, okay? Sensitivity is a synonym that means derivative. In economics, they use the word margin or marginal, okay? Marginal. If they use the word marginal, they're talking about derivative. So they don't say the derivative cost, but they mean the derivative cost. The word marginal or profit, okay? The marginal profit, they mean the derivative profit, okay? That's what they're talking about. Now, what it means, the significance is a cost function looks to the past. How much did it cost me to make the 100 things I just made? A marginal cost or a derivative cost looks to the future and says, how much more will it cost me if I make one more? Okay, so Bridge Club was out there selling horchata at lunch. Okay, how much did it cost them to sell the horchata that they had out there? Now, if they want to sell one more, then they use a derivative to look to the future. Okay, so keep that in mind, that one is past looking and one is future looking, but the future can only tell you one more. It's not like it's going to tell you 10 more. It's not going to tell you 100 more. It only tells you one more. Let me give you an example. This is our final thing today. Okay, someday you will be excited about buying a washing machine. Okay, it happened to me. Like, all right, so someday you'll have to buy one. All right, suppose that the cost of producing washing machines is this parabolic equation, this quadratic equation. Okay, so if I tell you this, if we figure out C100, okay, what is that going to tell me? Plain C.
How much it costs to make 100.
Okay, how much it costs to already make the 100 I've already made. Okay, can you guys type that into your calculator a minute and just tell me what that comes out to be? Okay, so it's going to be 2,000 plus 100 times 100 minus 0.1 and then 100 squared. Okay, as opposed to C prime 100, that's called marginal. Okay, in order to do C prime 100, you got C of 100?
I got 1,300.
1,300? All right, well, 13,000. Okay, so that is a past number. It has already cost me, got different answer? 11,000.
Oh, wait, no, wait.
That's okay, you'll just call that a Pfeiffer moment,
Yeah,
right? That's fine.
11,000.
Okay, 11,000 is good. All right, so let's find C prime. C prime is going to be 100 minus 0.2x. So let's find C prime of 100. So 100 minus 0.2 times 100. Okay, what's the answer to that? 80. The 11,000 looks to the past. It cost me $11,000 to do the 100 washing machines I've already done. How much is it per washing machine then?
500. That's like $1,000.
Okay. Okay. All right. Was it 11,000 or 1,100?
Wait.
Do I have an extra zero?
No, that was 11,000.
It's only like 110.
110.
Yeah.
Okay. Take off 2 zeros.
Okay.
Take off 2 zeros. All right. So the washing machines in the past, the total was 11,000. The cost per washing machine was $110. Now the person decides, should I make more washing machines? And they look to the future, and it says, if I made one more, it would only cost me how much more? $80. Okay, because you already have your labor, you already have all your materials, you already have, you've paid your rent, whatever. Okay, so it would be beneficial to maybe, that's the cost it's going to cost you to make one more. Okay, then you got to decide if your profit's worth it, right? We're just talking cost right now. We haven't gotten, maybe you can't sell it, and then you're stuck with a washing machine you can't sell, right?
We're not
Yeah.
going to talk about that in this class.
Of course.
Oh,
We're going to get there. Okay?
Are you going to do profitability?
No.
Would something like this be on the AP test?
Like, make a decision. Would you, having you do it for cost and having you do it for profit? And then should you go ahead? Should you make more, or should you just cut your losses to where you're at?
well, if you're selling them for $110, you could potentially make
We're not selling them for $110. This is the cost it costs to make it. You can set your price. Your price, that's different.
What's your price?
Okay? The selling is the revenue. That's different. Revenue is different than cost. Cost is the cost to actually make it. The cost to sell it, or the price to sell it, is called revenue.